So, we have seen a warm up so far of how to understand genome rearrangements using only one operation, which is reversal, right. A segment of the chromosome breaks and reverses and then fuses back. Okay. But reversal is just one piece of the puzzle, right. There are many other operations that happen when genomes mutate at a large scale. Another operation is called translocation that has an important role to play in cancer, and another could be fusion of two chromosomes into one chromosome or splitting one chromosome into two chromosomes. So, all these operations are important to understand how genomes evolve and how cancer or tumor genomes evolve from healthy genomes. Okay. And let us look at one such operation, translocation, in a bit more detail before we try to formulate the computational problem that covers all of these different operations and tries to generalize reversal distance to a distance that captures all these operations. Okay. So, there is this case in cancer in a tumor genome where there are these two chromosomes, a normal chromosome 9 and a normal chromosome 22, right, which splits at this locations, right. There is a split that happens at this location, it breaks at this location, and then these two pieces are swapped in position. Okay. This particular piece comes and attaches to chromosome 9, and this particular piece of chromosome 9 goes and attaches to chromosome 22. So, you will get a chimera like this, a mosaic of these two chromosomes, where you have a change chromosome where it is mostly 9 and then this end alone is chromosome 22, and then this chromosome 22 is very small to begin with. Now, it has become a mosaic of chromosome 22 here and then chromosome 9 over here. Okay. And this exchange of different segments of the chromosome between two chromosomes is called as a translocation. Okay. And this is pictorially or schematically represented in this case, where you have these two gene containing regions and they are being swapped, and you get this mosaic between chromosome 9 and 22. Okay. And this is not just between chromosome 9 and 22, there are thousands of rearrangements that are known and that has been documented, but it is best seen by looking at a particular picture called the karyotyping, right, where the normal cells, like each chromosome gets a different color staining, and so you can see that the normal color, all the chromosomes get distinct colors. Okay. But if you look at a cancer or a tumor genome such as MCF7, we have already seen this before, you can see that all the different colors are mixed up with each other. So, all the chromosomes have taken segments and then they have swapped segments with each other, and then you have a very mosaic genome, and this causes certain deleterious effects to the cells that makes them cancerous or tumorous, right. And so, it is of interest to not only understand reversals, but also these kinds of translocations that happen between different chromosomes. So, we have to generalize our notion of what is a reversal distance to a general distance that captures all of these operations. So, what are all of these rearrangement operations? What is the minimum number of such rearrangement operations that has produced MCF7 from a normal genome? Okay, that is of interest to us. To solve this problem, we need a mathematical representation of different chromosomes and the operations on these chromosomes, right? And that is what we are going to do next, so that we can then propose algorithms to solve this problem. Let us first try to represent these translocations. So, you have two chromosomes and then certain segments that are in the end of these chromosomes have swapped to get this mosaic chromosome, right, to again two other chromosomes. We are going to generalize our notion of sign permutation from a single sign permutation to one permutation per chromosome. Okay. And they are going to be represented within these parentheses. So, this is going to be the first chromosome, this is going to be the second chromosome, and then once you do a translocation, right, this plus 7 and minus 2 has gone here. So, we have 5, 9 and plus 7 minus 2, and then this 4 and 8 has come over here. So, they have swapped positions, 4, 8 and 7 minus 2 has swapped positions, right. So, this has now become minus 6, minus 1, plus 4 and plus 8. So, this is the mathematical representation of a translocation, where each chromosome gets a sign permutation within a parenthesis, like opening and closing parenthesis, and then the orderings will reflect what type of translocation has happened. And it is not just translocations, other operations like I said are possible. One is called fusion. So, you have 1 and 2 and 3, 4, 5 in these two chromosomes. If they both fuse, then it will become a single chromosome. So, instead of having two parenthesis expressions, you have just a one set of parentheses, one opening and one closing parenthesis containing all of 1, 2, 3, 4, 5. Now, if a fission happen, which is this overall chromosome split into two, then this single parenthesis expression, right, will become into two parenthesized expressions. Okay, 1, 2, 3, 4, 5 will become 1, 2 and 3, 4, 5. That is a fission operation. Okay. Now we have all of these operations: translocations, fusions, fissions and reversals. Okay. So we have 4 such operations. Now the question is again, given an input permutation which is in this multiple parenthesis form, they will call it as a multi-chromosomal permutation. So given this multi-chromosomal permutation, that is as the input, what is the minimum number of 4 operations: translocations, reversals, fissions and fusions, to transform it into a different permutation that represents the another species or another cell line genome. Okay. The problem now is to generalize reversal distance to this multi-chromosomal based distance using all these operations. Okay. More specifically, we are interested in something called the 2 break distance. Okay. In order to understand this 2 break distance problem, we have to first understand how these 4 operations, reversals, translocations, fissions and fusions, can be viewed as a 2 break instance. Okay. A 2 break is essentially an operation that breaks the genome at 2 places and then does some rejoining after that. Okay. And in order to do that, it is easier to view our genomes not as linear genomes, but as circular genomes, like every chromosome is converted into a circular piece. Okay. And what do I mean by that? We are going to basically take this first chromosome here and then like join the last gene and the first gene, or the last block on the first block. Similarly for the other chromosome, and view each one of them as circular chromosomes. Okay. And this will make it easier for us to understand what these 2 break operations are. Okay. And in order to do that, let us just also visualize it using a graph where there are 2 types of edges. The first type of edges is these black directed edges that represent actually the blocks, right, the gene blocks or the synteny blocks. So you have A here plus A because it is going in a clockwise direction, and then minus B is opposite orientation as A, so that is anti-clockwise. You have minus D, and then you have C is plus C, so that is in a clockwise direction. Here E, F, G, H, I, J are all in clockwise directions, right. So these are all the synteny blocks. Okay. Now I need to be able to tell what block is next to what block. Okay. So I add another set of edges called red edges. These are undirected edges. Okay. And that connect adjacent synteny blocks. Okay. So here A and minus B are next to each other, so that is added here, and then B and D are next to each other, D and C, and then C and A are next to each other. Okay. These are undirected edges. The black edges are directed edges because I need to be able to represent the plus or the minus signs. Okay. Similarly, here all of these are next to each other, so E and F, F and G, G and H and so on are all next to each other. This will also tell me that there are 2 chromosomes involved, 2 circular chromosomes involved. So this is a nice pictorial representation. Okay. And this graph is drawn in this way. The same graph can be redrawn in other ways also, and that will help us understand the different operations that we can do on these graphs. Okay. So let us look at 2 different ways of drawing the same graph. So here is the original graph that we have drawn, A minus B minus D C. The same representation, the same graph can be drawn a bit differently, where the positions of D and C are swapped. Okay. Because A and B are next to each other, you still have the same link like this, but B goes to the head of D, right. So then that is shown here, D is not here anymore. So then this will be the link that you have. Then you have the tail of D and the tail of C that are connected. So that will be this one. Then you have the head of C and the tail of A that are connected, which will be this one. Okay. This is just simply a different way of drawing the graph that will make it easier to understand our 2 break operations, but the permutations are exactly the same. Okay. Both of them are the same representation for Q, it is just drawn differently. Now that we are comfortable with the graphical representation of the circular chromosomes, let us just see what happens when a reversal operation happens and it actually changes the permutation. Okay. A permutation P shown here changes to a new permutation Q. Okay. By reversal of a segment minus C and D. Okay. Minus C and D has now become minus D and C. Okay. And how is it going to change the structure of the graph? You will see that most of the parts of the graph will remain the same, but wherever the reversal is breaking and reversing, only those parts, those nodes and edges will be involved. Okay. Will be changing. Okay. You can see here that A and minus B, A and then minus B are the same in here as well as here. So that will also be the same here and here. Okay. That A and minus B is the same. Now after minus B comes minus C here, but then here you have minus D. Okay. So there is going to be a new edge that comes here. It won't have this nice circular arrangement, but this reversal will add this particular edge. Okay. And then after minus D, then within the block there is nothing changing. So then this D and C will be linked as before, but now C was connected to D before, but now C is going to be connected to plus A here, right, and so you are going to get this particular one. So, you can see here that these two edges has been broken, the ones that are indicated by a star, and then these two new red edges has been added. Okay, that is what is written here. A reversal deletes two red edges and replaces them by two other red edges on the same 4 nodes. These are the 4 nodes in the graph, the first node, the second node, the third node and the fourth node. Okay, these edges are removed and then these edges, these two edges are added on the same nodes. Okay. That is what has happened when a reversal happened. Now, we can see why a reversal is called a 2 break. Two edges are broken and then two other edges are inserted on the same 4 nodes. Okay. Now that we have seen that the reversal can be viewed as a 2 break, now let us see how a fusion or a fission works. Okay. Let us look at fission. It is actually simpler to think about than reversals, because what you have is a single chromosome A minus B minus C minus D is going to be split into 2 chromosomes, a fission into 2 chromosomes. Chromosome 1 is A minus B and chromosome 2 is minus C and D. Okay. And we can see that the representation of this A minus B minus C D, the representation of P is shown on the left hand side. The same representation will be shown here, but there will be two cycles, right. So, you have A and B is the same, but instead of B connecting to C, B is going to come back to A, because there is only A and minus B in the first chromosome, right. So, then that is going to come back to A. Similarly, in minus C and D, we are going to have a cycle that involves only minus C and D, right. So, you have this one cycle that has been split into 2 cycles, and again the same kind of operation is happening. You have these 2 edges over here that are being broken, right, and then 2 new edges are being added here, right. So, there is 2 edges broken and 2 edges added. Okay. So, that is what is shown here. The stars represent the edges that are broken, and then there are these 2 new edges that are added. So, a 2 break is a rearrangement that replaces 2 red edges with 2 new red edges on the same 4 nodes. Okay. That is why a fission can also be viewed as a 2 break. Okay. And fusion is just the opposite of a fission. So, it just goes from the right hand side graph to the left hand side graph, right. And so, that is also basically you have these 4 nodes that you are looking at, and then fusion will basically remove these 2 edges and then add these 2 edges, right. And so, there are always, whether it is a fission or a fusion, and we have already seen in reversal, 2 edges are broken, 2 edges are added on the same 4 nodes. Now, let us look at the final part, which is translocation on linear chromosomes. We can first circularize the chromosomes and do a 2 break operation and then linearize it again. Okay. I am going to spend a bit less time on this. You can take a look at it to understand that it is also a 2 break operation. Okay. So, you first circularize the chromosomes. So, these 2 chromosomes are linked together by adding this to this and then adding this to this. This is the place where the D and A are glued, and this is the place where the H and E are glued. Then you do a 2 break operation to do a translocation, and that basically again involves breaking these 2 edges and then adding these 2 new edges. This is added, this is subtracted, right. These are removed and these are added. Okay. And then now wherever you had put a glue, you can linearize it again, and you will get these translocated chromosomes, where you can see here that the BCD, B minus C and D has been translocated to the other chromosome. Similarly, F minus G and H has been translocated here into F minus G and H. Okay. So, in this view, a translocation is also a 2 break. Okay. So, what we have shown so far is all of these operations, which is reversals first we saw, then we saw fission, and the opposite of that is fusion, and then we saw translocation. All these 4 operations can be viewed as a 2 break, where you look at these 4 nodes in your circular representation, multi-chromosomal representation, and then you remove 2 red edges and then add 2 more red edges. Okay. And now we are ready to define our break distance problem. A 2 break distance between 2 multi-chromosomal permutations P and Q is the minimum number of 2 break transformations of genome P into genome Q. Okay. And essentially then that is called as a 2 break distance. It generalizes the reversal distance, and the problem is you are given these 2 genomes on the same set of synteny blocks, and then you want to figure out the 2 break distance to transform one to the other in a minimum number of 2 break operations. Okay. Now, how do you solve this problem? Okay. That is what we will look at next, using the concept of breakpoint graphs. Okay. we have already set up some initial formulation of the breakpoint graphs of the two individual permutations. We have to somehow combine it into one graph and then try to solve the problem that way. Okay. And so, how are we going to do that? We are given the circular representations, multi-chromosomal representations of two permutations P and Q. Here each permutation is only on one chromosome for simplicity, but it will also extend to multi-chromosomes. Now, we want to combine this both into one graph. To make sure that it happens that way, then we have to make sure that the ordering of the synteny blocks, the black edges are the same. Okay. So, the Q I can draw it either this way as a circle, or I can also draw it in a way that there is A, B, C, D the same way that P is drawn. Okay. So, I can just draw this Q using the same ordering, which is this A, B, C and D in P. So, I have this A, B, C and D in the same orientation as in P. Now, I will use the blue edges appropriately to connect it. Okay. The head of A is connected to the tail of C. So, this head of A will be connected to the tail of C over here, right, and then the head of C is connected to the tail of B, head of C is connected to the tail of B and so on. Okay. Once we have a way to draw Q using this equivalent representation, but a different drawing that aligns better with P, then we can overlay P and Q on top of each other to get something called as the breakpoint graph. Okay. The breakpoint graph is simply the union of edges in the circular representation of P and the circular representation of Q. Okay. And then this breakpoint graph has some nice properties. And then now this has some interesting properties, this breakpoint graph. If you look only at the red and black edges in the breakpoint graph, right, then you will get back the first permutation P. If you only look at the blue and black edges, right, in the breakpoint graph, then that has the target permutation Q, right. And then if you look at the colored edges, the red and the blue edges, then you can see that it has some sets of cycles that it forms. Okay. No two blue edges are adjacent to each other, no two red edges are adjacent to each other. So, it is always alternating, and so you get these alternating red blue cycles. Okay. And the number of cycles, let us just give it a notation. So, cycle of P comma Q is the number of red blue alternating cycles. In this particular example, you have one cycle which is this BC and another cycle which is formed with this A and D, right. So, you have these two cycles here. And then the number of cycles says something interesting about how similar P and Q are. Okay. We will see in the next few slides that if the cycle number is higher, then P and Q are more similar to each other. If it is smaller, then they are more farther from each other. Okay. Why is that? Let us look at one more example before we establish that fact. What is the cycle of P comma Q in this particular case, where P is the first permutation and you want to convert it into Q, which is another permutation. Again, remember that these are multi-chromosomal permutations. So, you have two circular representations for each of the chromosome in Q. Okay. How does this one chromosome and ordering in P get transformed into these two chromosomal orderings, two chromosomes and their corresponding orderings in Q. Okay. And in order to understand it, we again take the union of the edges in both of these, right. We just redraw Q so that it is easier to take the union and overlay P on top of Q. So, this is just exactly Q, but redrawn in a different way, right. And then we overlay both of them. So, this is the union of these two circular representations of P and that of Q. You have the breakpoint graph. If you look at the particular colored edges alone, okay, the red color edges for P and the blue colored edges for Q, you will see that there are three cycles here. Okay. One cycle is over here. Maybe I will change the color here. So, one cycle is over here, another cycle is over here, right. So, this is cycle 1, this is cycle 2 and then the remaining one is cycle 3. Okay. So, there are three cycles here. Okay. So, in this example we had three cycles. Let us look at what maximum number of cycles we can get in this example or in a general example. Okay. Let us just look at a simpler example where there are 4 blocks, okay, and then you have the P that is drawn in this way. Now, what should be the Q that will maximize the cycle of P comma Q? Okay. And if you think about it for a bit, you will realize that the maximum number of cycles you can get is the maximum number of red edges here, right, because the smallest cycle you can get is one red edge and one blue edge, right. So, let us just make that one red edge and one blue edge here. So, you have one red edge and we have one blue edge, you can have one red edge and one blue edge, one red edge and one blue edge and similarly, right. If each of the cycle is the smallest cycle you can make with these two edges, then that will give you the maximum number of cycles. Okay. but these blue edges that I have drawn are exactly identical to the red edges. So, the q that maximizes cycle of p comma q is actually going to be p itself. So, what we have here is the maximum number of cycles will happen when q is set to be equal to p, and it will be equal to the number of blocks in either of these permutations, right. And the number of blocks here is the number of red edges or the number of blue edges, that is 4, and so that is the maximum that we can get in terms of the number of cycles. Okay. This gives us an idea on how to design an algorithm to come up with a set of 2 breaks that will transform one permutation p to another permutation q. Okay. Let us just see what that idea is. So, what we have is that the series of 2 breaks that we want to figure out increases the number of cycles from 2 to 4. Let us just look at the exact 2 break operations that will achieve this in the next slide. So, we have the starting permutation which is p, and then the ending permutation which is q, and then an intermediate permutation which is p prime. Okay. When you look at p, you have this particular breakpoint graph representation, right, and then you are going to do a 2 break operation where you are going to remove these 2 starred edges, look at the 4 nodes that are incident to these starred edges, right, and then rewire it in the sense that you add 2 more edges, one edge that goes like this and another edge that goes like this among these 4 nodes, okay, and that is what is shown as p prime here, okay. And what happens to the number of cycles? Initially the number of cycles was 2, right, so that is shown here, and then now we have 3 cycles that are here, right. So, we have this cycle over here, the second cycle over here, and the third cycle in the middle, okay, and so you have the number of cycles has now become 3. Okay. So, that is good, that is progress, because you are getting a permutation p prime that is closer to q. As the number of cycles increases, we are going to use it as a measure of how close is it to the target permutation q. Now, the next operation is that this cycle and this cycle are already in an identity format. So, we just need to convert this middle cycle into 2 cycles which are in the identity format. So, we are going to break these 2 edges, remove them, and then add 2 more edges, which is this and this. Okay. And that is what is shown here in the final one q, right, and then so you have a p double prime which has now become equal to q, and then so you have 4 cycles here, and then we have completed the 2 break operations that will transform p into q. Okay. This is for this particular example, and a natural question is, can we design an algorithm that will work for any p and q? Okay. And for that we are going to use both a lower bound on the optimum and also a solution that will attain the lower bound. Okay. So, we are going to say that the optimum is going to be at least some lower bound, and this lower bound will be expressed in terms of cycles and blocks, okay, cycles and blocks in the breakpoint graph, right. And then we are going to say that the solution can actually achieve the lower bound. So, then this implies that we have a solution which will have the same cost or the same objective function as the optimum, okay. And so, that is what we are going to achieve using this 2 break distance. If you remember that the breakpoint theorem and the sorting by reversals, we were not able to show that fully, even though there are algorithms that exist for figuring out the reversal distance and the sign permutation. Here we have a more general set of operations using 4 operations like translocations, fusions, fissions, and reversals, all of which can be represented by 2 breaks. And with these 2 breaks, we not only establish a lower bound, we are also able to achieve that lower bound. And so, we have an algorithm, we will show an algorithm where we can calculate the optimum number, the minimum number of 2 breaks that will transform one permutation to another. Okay. Let us go ahead with this. So, we have a p and q and a set of 2 breaks. We want to sort p into q using a series of 2 breaks, or in the notion of breakpoint graphs, we want to operate on these add and remove red edges, right, in these breakpoint graphs, so that you go from smaller number of cycles to the maximum number of cycles, which is the number of blocks. Okay. So, cycle of p comma q, a series of 2 break operations which increases, and then you get cycle of q comma q, which is equal to blocks of q comma q. Okay. And so, the number of red blue cycles has to increase by this final amount, right, cycle of q comma q has to increase up to this blocks, right. So, blocks of p comma q minus the current value of cycle, right. So, initially in the example that we saw, this was 2 and this was 4, right, the blocks was 4. So, we had to go from 2 to 4, or we had to increase the number of cycles by 4 minus 2 equal to 2, right. In a general case, we have to increase the number of cycles by the maximum number of cycle blocks of p comma q minus the current number of cycles cycle of p comma q. Okay. the maximum increase in the number of cycles that each 2 break operation can contribute. Okay. So, in these 3 examples, in these 3 particular examples, we have seen that the number of cycles that can increase due to a single 2 break operation is at most 1. Okay. But is it true in general? That indeed turns out to be the true. We can formally see it in the following way. Okay. If you have the number of cycles that are increased, you want to get what is the number of cycles that is increased due to a single 2 break operation. Okay. That is going to be the number of cycles that is created due to the 2 break operation, new cycles, okay, and then minus the number of old cycles that are destroyed, right. And I want to get an upper bound on the number of cycles that are increased. Okay. So, which means that the number of new cycles created, I am going to argue that it is going to be at most 2. Why is that? Because you are adding 2 new red edges, right. So, you are adding 2 new red edges, and that can participate in 2 different cycles. Okay. There is no more red edges that you are adding in a single 2 break operation, right. And so, this number of new cycles created can be at most 2. Okay. And the number of old cycles destroyed, we need to have a lower bound on that, because you are removing 2 red edges, right, and then that can participate in the same cycle, and you are destroying at least 1. Okay. There may also be 2 cycles that you destroy, but at least 1 cycle you will be destroying by removing 2 edges. Okay. So, this is going to be at least 1, but because of this negative sign, this overall at most remains the same. So, you have 2 minus 1, and that is equal to 1. Okay. So, we have the number of cycles is at most 1 due to a single 2 break operation, and this directly tells you that the optimum is going to be, this optimum is going to be at least this lower bound that we talked about. It is going to be like we need at least as many, right, because each of them only increases by at most 1, we need at least as many operations as blocks of p comma q minus cycles of p comma q. Okay. Because you can only improve the number of cycles by at most 1 in each single break operation. And then we do have actually that gives you the lower bound, but we also have a 2 break that will increase the number of cycles by 1, which is this particular second operation, right. You can always choose 2 red edges and then remove them and then add 2 other red edges that will increase the number of cycles by 1. Okay. So, we have both a lower bound which says that every 2 break can only increase the number of cycles by at most 1, which means that the optimum is going to be this particular lower bound that we have shown here, right. And the solution can also reach this lower bound, which is blocks of p comma q minus cycles of p comma q, where it matches the lower bound, and so opt is equal to solution, because you can always choose this particular operation and increase the number of cycles by exactly 1. So, what we have is that a 2 break increases the number of cycles by at most 1, there exists a 2 break that increases the cycles by exactly 1, right. And so, this gives you a lower bound on opt, this gives you the actual solution, right. And then exactly the lower bound is this, and the solution is also this. Okay. So, every sorting by 2 breaks must increase the number of cycles by blocks of p comma q minus cycles of p comma q, right, and that is also achievable by this exact solution, right, where you just increase the cycles by 1 each using the second operation that we showed in the previous slide. So, the 2 break distance theorem is essentially this this formula here that shows that the 2 break distance between p and q is equal to the number of synteny blocks in p and q, the common synteny blocks in p and q, right, minus cycle of p comma q, which is calculated as the number of cycles in the breakpoint graph of p comma q using only the blue and the red edges.